Hi everyone, welcome to Altitude STEM Club YouTube channel. Understanding scientific phenomena by doing experiment is my passion. Today, let us do an experiment performed by Chirstain Oersted in 1820. He discovered that a current carrying wire has a magnetic field around it. For doing that experiment, we require two things. One is a current carrying conductor and another one is a magnetic compass. It's also interesting to know that in 1800, Alessandro Volta invented the first true battery, which came to be known as voltaic pile. It's almost 20 years to establish the relationship between the electricity and magnetism. All the experiment conducted by the scientists before 1800 was restricted to static electricity. Regarding magnet, human being knows about the magnet long time ago. But in 1600, William Gilbert discovered that our planet has two magnetic poles. He was the first person to fully explain the working of a magnetic compass. If you see the chronology, the magnetic compass was in 1600, battery was in 1800, and the relationship between the magnetism and electricity was in 1820, and that experiment is what we are going to do today. According to Oersted, when a current carrying conductor, if we have a current carrying conductor, it has a magnetic field around it in the form of circle. The direction of the magnetic field is given by right hand thumbs rule. The thumbs should be pointing towards the direction of the flow of current in this way, and the thumb is in the direction of the current and the fingers will give the direction of the magnetic fields. The magnetic fields are circle and concentric, and it has developed around the current carrying wire. Let us do the experiment. For doing that experiment, I have already set up. So I have a compass, magnetic compass here, and I have a copper wire. We are going to pass the current through this copper wire. The position of the compass is in this form, is in the vertical form. The north pole is on the top, and the magnetic needle, north pole is on the top, and the south pole is on the bottom section. I'm going to pass the current in this direction from this to this. So from bottom to top, I'm going to pass the current in this direction. It means that I am going to connect the positive on this side and negative on this side. And I'm going to use a simple battery which will allow the current to pass through this copper wire. So let me connect, let me put on the key. When I connect it, let us see what happens. So when I connect it, the magnetic compass needle deflects. In which direction does it deflect? It deflects from the left to right. The magnetic compass needle deflects from left to right. Let me release the key. I have released the key now, and it is in the normal position. The normal position is the north is in the top and the south is in the bottom. So let me do once again. I have connect the key now. The needle is in this position. It means that in this position, the north is in this position and south is in this position. So let us try to understand and let us try to get a clear picture why the magnet is deflecting from the left to right. So let us see. Now, this is a current carrying copper wire, let us assume, and I have a magnetic compass needle which is in this form. North is on the top and south is on the bottom. So it is like this. So and the current is flowing from the bottom to top. So for time being, let us remove this copper wire and then let us try to hold it like this. So now the magnetic field, for a bar magnet, the magnetic fields originate from the north poles and terminates toward the south. So the magnetic field has a direction. So if the direction is from this side to this side, so it means that we can consider my tip of the finger is the north. So if this is the north, then the top position is north. So north and north, like poles, repel each other, but unlike poles, attract each other. So every portion of the magnetic compass needle is experiencing an magnetic field which is developed by the current carrying copper wire. So if I consider this point, so this is a north, and so my tip is north, so obviously north and north pole reflect, so this will reflect. But the magnetic compass has a pivoted point at the center of the needle. So this portion is connected to the pivoted point. So if we consider the lower portion, in the lower portion this side is south, my tip is north. So unlike poles attract each other. So this portion will tend to attract and this portion will tend to repel. Due to the setup of the magnetic compass and it experience two equal and opposite force on the tip of the needle, so it moves in this way. So if we do like this, it will move this way, repel. If we do like this, it will attract. So this is why the magnetic compass needle deflect in this direction when the current is flowing from the bottom to top in this position. Now let us change the terminal of the battery. It means that let us change this, let us make this side as positive and this side as a negative. Then the current will flow this direction. So let us see what happens to the magnetic compass needle. In which direction does it deflect? Let us see. So let me change the terminal. So I'm changing the terminal and let me connect the key. So let me see, now I have connected. Now the magnetic compass is moving from right to left. Let me release the key. I have released the key. Now it's in normal position. The normal position is nothing. The north pole is on the top and south pole is in the lower section or in the bottom portion. So now let me put on the key again. Now I have on the key. So now the magnetic compass deflects from the right to left. It is like this. Again, let us try to understand this behavior. So again, this is a current carrying conductor and this is a compass needle which I have. So it is like this. So when I remove this and then when I hold it like this, if you see it, it's a circle, it's in the circle. So it is like this. So it is like this. So this tip is north. So north and north will repel and north and south will attract. So if this is repel, so it becomes like this. It moves in this way. And this side, it becomes unlike poles. Here it becomes like pole. Here it becomes unlike pole. So like poles repel each other, unlike poles attract each other. That is why when I make this side as positive and this side as negative, it means that the current is flowing around, it deflects in this direction. So the magnetic field which is developing around a current carrying conductor is for this whole length. So the magnetic field of the current carrying conductors interact with the magnetic field of this compass at each and every point. So here it is like poles repel, unlike poles attract. Due to the behavior, due to the pivoted point of the compass needle, two opposite forces are acting on it, so it moves in this way. So this is what Oersted did in 1820, and he discovered that a current carrying conductor has a magnetic field around it, and the magnetic field is in the form of circle. This is what he did in 1820. Now let us try to do one more experiment. In this experiment, what we are going to do is, I have cut the aluminum strip a very thin in this form. So aluminum is also a good conductor. So if I pass a current through it, obviously it will have a magnetic field around it. when I pass the current from here to here, if I do like this, it will have a magnetic field. But if I bring it up and then if I hang it like this, and if I pass the current, what is the behavior of this aluminum strip? That is what we are going to perform the experiment. So the current is flowing from here, and after reaching here, and it turns back. So this side the current is flowing in this direction, and in this side the current is flowing in this direction. So we can consider this as a two wire which are parallel to each other, but the direction of the current are opposite to each other. One is in this way and one is in this way. The setup I have already done here, so you can see a small aluminum strip hanging, from here, and it is in the U shape. And when we pass the current, let us see what happens. Just now we have discovered that from the experiment, a current carrying conductor has a magnetic field, and the magnetic field is given by right hand thumb's rule, and the field is in the circular concentric circles. So let us see how it, I am going to put this one so that it doesn't, you can see the strip properly. So let me pass the current through it, and let us see what happens. So when I pass the current, can you see what happens? The two aluminum strips repel each other. Can you see? I will just repeat the experiment once again. So on, repel, off. Let me do once again. On, off. On, off. So here in this experiment, when a two current carrying conductor kept parallel to each other, and when the current is flowing in opposite direction, the wires repel each other. The wire repel each other. So the current passing through this produce a magnetic field, and the current passing through this produce a magnetic field. Two magnetic fields interact each other and develop that repulsive force. So try to understand that experiment. I have done it with the explanation which I have given from the Oersted, and try to understand how that happens in this aluminum strip, why it, try to understand and try to get the interaction of the two magnetic fields. So this is extra experiment which was not a part of Oersted. I just demonstrate it so that you can understand the interaction of the magnetic field developed by two current carrying wire. I am using the aluminum strip, very small aluminum strip. I cannot pass more current, because if we pass more current, the aluminum strip will burn. That is why I am not able to demonstrate the force, the repulsive force, the very strong repulsive force between the wire, because if I pass more current, then the aluminum strip will burn. So because of that, I have adjusted the current in such a way that I can just demonstrate a little bit. So this is one. So we can do another experiment where we can see what happens when a two wires parallel to each other, and when the direction of the current is in the, when the direction of the current is flowing in the same direction. When the current is flowing in the same direction, what happens? So that can also be done as an experiment. But right now I have done, so it is a two wire which are parallel to each other, and the current are flowing opposite. The direction of the current are not same, means opposite to each other. So when we pass the current, it repel each other. So the magnetic field of this interact with the magnetic field of this. Because of that, it repels. Thanks for watching my YouTube channel. Thank you.